scale. Like
Good. And what does that mean? What is the mean free path? Like, what are we talking about?
the longest distance you can go without hitting stuff.
Very close. I wouldn't use the word longest, but like an average distance. Yeah. Okay, good. And then what do we mean by length scale? It's a specific one. It's what? Constraints. By what? Yeah, it's arbitrary in what respect? Like arbitrary as in like a 5-year-old chooses it, or arbitrary as in
I guess arbitrary on like setting you're using it in.
okay, so we choose it for the setting, right? It's not predetermined. We'll talk about the length scale in more detail. What's a mean free path? Well, we looked at that picture before of these things. Would you know how to calculate a mean free path? Have you ever done that before? Can you guess how you would? What?
How much space between all of them?
So you'd have to do the measurement? Could you construct it any other way?
Pick up the space and divide how many things are in there.
Yeah. So think about how many particles there are. So let's think if we have a length. This chunk sucks. I'm sorry. This is already gonna be bad. If you have a length, how do you get other things that you might know about the particles? You smash together. So you want a length time between particles. What might go into that length? What things might be important? How many there are, because that might tell you the spacing between, so the number. Or maybe even better, the number density, right? How long, what the time or?
Yeah.
Yeah, time might be getting to the same thing that I want to get to, I'm kind of hinting at.
Yeah.
Yeah, and so if we combine length and time, you get. Length and time, yeah, how can you combine those to make another variable? Which is? Velocity, there you go. Yeah, so the mean free path or the mean free speed or the velocity of the particles might be important. And so similarly, we might have something like the temperature. Right? Temperature is usually a representation of the speed of the particles, right? So we'll come back to that idea in a little bit. Just to warm up our brains, what is the first derivative conceptually? Slope. Second derivative is the curvature. Curvature. How do you find the maximum or minimum?
Find the maximum function equal to 0.
Not the function.
I mean
The first derivative.
right. Yeah.
And then how do you determine whether that is a maximum or a minimum?
Curvature of sign.
The curvature gives you the sign, correct? So you find the second derivative at the point that you found the maximum, and you check whether it's positive or negative. Good. All right, so here's the continuum hypothesis, and we're going to look for locations when it is not true, when things are not gases. What happens at the top of the atmosphere? Yeah, particles bounce around up there, sure. The top of the atmosphere is a little unusual, right? Way down here, we're definitely in a fluid. The very top of the atmosphere, there is a transition into nothing. Right? So you have some particles that will just go and never come back. Which means that their distance to hitting something else is equal to or larger than the scales that we care about. Is that a fluid? Let's go back one step. What is the definition of the Knudsen number? When is it a fluid? Let's think about the hallway. Sorry, go ahead.
We do have a mean free path. We do have a chance of colliding.
Yeah, so you always have a chance of colliding, right? So the question is, it's the ratio of these two numbers. If we think about our example of leaving a basketball game, okay? If the mean free path is larger than the length scale, like in this room, I can walk and I can just hit a wall, right? Then it's very clearly not a fluid. But if you bump into a lot of people as you're trying to leave, then you might say, oh, there's fluid-like properties. It almost looks like a continuum. I see waves that propagate as one person stops to bend over and tie their shoe that creates a wave that travels backwards, right? So what's the requirement that we have here on the KN?
To not be.
Greater than 1 to not be a fluid, and much less than 1 to be a fluid, right? Okay, so let's go back here and let's think now about the top of the atmosphere. Would we consider that a fluid in this context? Not necessarily, right? Okay, what about supersonic flow? We haven't talked about that yet. What about the flow around a single-celled organism? What happens at the bottom of the ocean? Yeah, super high pressure. Is that invalid? Can you consider that a fluid? The pressure's high? Yeah, probably. What about narrow flows? Like think about really thin pipes. Does that break the continuum of orifices? I guess we'll see, right? Okay. Okay, we saw that. So we are going to use some different definitions here, and we need to learn them. What is V and what is U? V represents all possible velocities, and U is the average. So we talked a little bit last time how we had this little box, okay? And you could imagine a bunch of particles in the box going about in many different directions, okay? And each one of them will have an individual velocity. So their individual velocities will be V. But the box as a whole might be moving. And we're going to describe that with U. Does that make sense? That's really important because when we think about how we want to characterize fluids, even in the abstract sense, we have to think about how bulk motions and individual motions lead to all of the phenomenon we see, right? If we talk about something like the word pressure and the word strain and the word stress, those things all emerge from the fact that there's only little molecules bumping into each other, right? Do we know what the Maxwell distribution is? Have you ever seen those words in that order before? Do you know what it looks like? Sure. Yeah. It's a distribution of speeds, good. And so what would it look like? It's a probability distribution, right? Or it's a frequency distribution, right? So it's saying something like some number of atoms have a specific speed.
So like Gaussian?
Is it?
I don't know.
Yeah, if it was Gaussian, we'd probably use the word Gaussian, right?
Yeah.
Every time if you're special enough to get a name, it's probably a new shape. But it's gonna start by looking kind of Gaussian. Okay? It's gonna be centered around a speed that we'll discuss in a few seconds. And it's gonna go up. You're gonna think, what is Gaussian? What the fuck, bro? And then which way does it drop? Down? Just exactly like that?
I feel like it'd be steep.
Steep? Okay. It's actually this way. There's a really long tail. And this comes from the observation that if you have a particle and it's bouncing around in a gas, it's very hard for it not to move. So this is zero velocity. That's very unlikely. It's probably moving a little bit. But what's interesting is that there's a probability that it moves really, really fast. That a bunch of collisions work together to increase the individual velocity crazy. Okay. So this is the frequency, you find it in your book as equation 1.1 of finding some number of particles with the velocity v. That's the individual velocity v, right? Do you know what a moment of a distribution is? Okay. What?
Is that like an occurrence?
When we do, have you taken quantum mechanics? Okay. So if you're in quantum mechanics, you have operators. And you apply operators on something called the wave function, and that tells you something about the particle of the system that you're looking at. So for example, in quantum mechanics, you operate on psi to maybe find the position, right? And you use a position operator to find out where the particle is likely to be. Does that make sense? Similarly speaking, we can take moments of a probability distribution. So quantum mechanical psi is a probability distribution. It's telling you where they think the probability will be. And similarly, we can apply to a Maxwell distribution, you can apply operators. Okay? You have the first moment, the second moment, and the 0th moment. And they each tell you something about the distribution as a whole. Okay. So here's the Maxwell distribution. And you can see what I've done here is all I've done is I've just changed how fast this velocity is here. As the velocity increases up to 5 from blue to green, blue to red to green, it changes the shape, right? And it broadens out the Maxwell distribution. So you can see it's peaked, and then there's that little tail here that Maxwell tells important. Okay. Here's our mean free path estimate. We get that from this. Okay. So you have the average distance traveled. Sorry, the average speed times time is the average distance traveled. You have the volume of an interaction, and then the number of particles in a volume. So essentially, you have the distance traveled divided by the total number of particles, and that's something like the mean distance per collision. Okay. Where this is your length scale, that's the side that you chose, and that's the number of particles in the box. Okay. Let's talk about molecular transport because that's really important. When we think about any type of fluid, there's multiple things in it. So whether you think about it just in terms of maybe some mix of oxygen and nitrogen, if you start with nitrogen on one side and oxygen on the other, they will mix, right? The oxygen will diffuse through until the number of states that it is encountered has the highest entropy. So this in StatMech. People taking StatMech? Not yet. Okay, so StatMech shows the direction of time. So what that means essentially is that if I take something like this glass, imagine a glass, and I dropped it and fell on the ground and shattered, and you watched a video of that happening, you could tell which direction it was being played. Because if I reversed the tape and I showed it all come back together and then go upwards, but I flipped it over, you'd be able to tell that it was being played backwards. Similarly, when we ran that picture, or we had the picture on Monday of water that's flowing, you couldn't tell which direction it was going. Because you could say, well, it could be flipped over and it's going in the opposite direction, right? So when something is destroyed, for example, you see it goes from an ordered state into a disordered state. And similarly, if you have oxygen on one side and nitrogen on the other, that is an ordered state. And then the disordered nature of the interactions leads to the most equitable situation afterwards, right? Similarly speaking, molecules will move stuff. Okay, so they have interactions like surface tension. We saw that in the object's surface tension that we saw in the spheres. And they also will create gradients, whether that is through like saltwater gradients. Have you ever seen them before? So you might have like an estuary or a river that's flowing out to the ocean. So you have fresh water feeding into salt water. And then you have a physical boundary in the water, which looks like this. Okay, here's the seafloor. Here's water. This is fresh. Here's the ocean. Not right the ocean, let's just write outside. Here's the ocean. That's salty, right? Which one's heavier? Right? So what you have then is you have this like, depending on how fast it's moving, right? You might have like an inflow like this, and you have a chemical gradient. So you have fresh water here, salt water here, and they don't want to mix unless you like stir them up. So if it's not moving very quickly, they're just going to sit on top of one another until you set up these gradients, and then you molecularly transmort osmosis, for example. You've heard that one in biology class, and transport of salt across gradients. Okay. We talked a little bit about second derivatives, how they talk about shape. If we were to think about them in terms of the equations that govern them, have you ever seen the diffusion equations? The diffusion equation is straightforward. It has some function df dt, the rate of change of that object, okay, is only given by minus d, the diffusion constant. Can you read that? Diffusive. So it's like it measures how quickly it's diffusing. df x. But what have I written? Let's imagine that you have something over here. This is f. Right? Of x. Here's x. And on this side, I have a lot of it. On this side, I don't. Okay, so the rate of change of this function is due only to its shape. Specifically, its curvature. And it wants to go in the opposite direction of the curvature. What does that mean? So here it's flat. What's the rate of change? 0. Good. So there's no change here, right? So it's flat and it's flat. Nothing happens. So where's the interesting stuff? The boundary, right? So it's right here, right? There's a sharp discontinuity. So this has high rate of change, right? This side here wants to become larger, and this side here wants to become smaller because of the negative. Okay? So the very first thing that happens is that you curve. Right? Okay, but now I have curvature. So now this boundary moves out. Right? And it starts curving more. Okay, so now, oops, did that wrong. He did it, right? And eventually, right, it keeps doing this. What's the goal of the diffusion equation? What does it want to be? What? To diffuse all of them. It wants to be here. Because what's the curvature? And then it's in a steady state situation. Okay. So that is diffusion. You'll need to know that. So this diffusion is created by molecular transport. Individual molecules bumping into one another. This is different than bulk flow, right? So far, we talked a little bit about this thing V, and we talked about this thing U. We're not talking yet about U, how we're going to see it in fluids. We still are only describing the things that V can do. V describes the mean free path. V describes how much collisions are occurring in the gas or the fluid. And the rate of the transport affects the concentration rate. So just like you see there, that D, whether it's the diffusion, right? How strongly this gradient is peaked or steepened is due to the rate of molecular transport. And if you think about molecular transport as things bumping into things, then you see that that goes back to which concept?
Statistical. Yeah.
Something we talked about earlier today, a couple slides ago. The mean free path, right? Things bumping into things is what does the diffusion. So the rate of molecular transport is directly affected by the mean free path. You're not wrong, Dave. I just wanted to draw that back. Okay. Yeah. Does that make sense? Okay, so we're going to talk about a lot of details about this. We'll look at some like advection diffusion equations, the difference between fluids moving versus fluids just moving molecularly transporting things around. Here is an example. Okay, here is a very nice curve of something called y. Y is a function of y. Very good. The mass flux and the heat flux describe a negative gradient with respect to space. We saw that right here. Will this work when we want to describe the molecular transport? Why not? So yeah, so let's say that this is heat. Right? This is high heat versus low heat. Could this be described by diffusion in the way that heat is going to transport from one to the other?
You could show like equilibrium. But I think that's like maximum or minimum, right? Like in that graph, that's the 100% diffusive. I don't think that is 100% to the minimum.
Well, so the question is let's imagine that this is not a fluid. Let's imagine this is a metal. And I heat this up, but I heat it up with this curve. Right? This is the distance, and this is the heat. Right? So it's not uniformly heated, and it's not heated like we had some example where they were just one was hot, one was cold, never in contact, kind of smoothly heated. So how does heat now travel? Let's say it's an iron bar made of metal. How does heat travel in that iron bar? It diffuses, right? But it diffuses through which process? Is it through radiation? Is it through... This has a physical mechanism, right? What's that?
Are you heating it or is it just already hot?
So I heated the rod up in a very special oven that somehow made it curved in temperature. And then I transported it to a vacuum room where it's not in contact with any other particles. And now I claim that something will happen. Heat is uneven. How will the heat travel in that rod?
Given it's lost in the environment.
But it's in a vacuum.
That's just.
So let's imagine you have a cast iron. You're cooking some breakfast. You heat it on the bottom, but the handle gets hot. How's that?
So it will just spread out evenly throughout the metal until it's even at all places.
Yeah, that's the process of diffusing. But my question is, what is the physical mechanism? What about the metal causes the rest of the metal to get hot?
Sliding across.
Molecular collisions, right? So I'm just trying to drill this in, right? The today's class, we haven't talked about any of how the fluid moves, is about the fact that everything we're talking about is molecules, right? Okay, so if molecular diffusion works for the heat equation, I'm gonna tell you ahead of time, it works for the diffusion equation, right? And there'll be small tweaks on how we decide it responds to the shape, right? Some respond to the gradient, some respond to the curvature. We'll see that in different contexts. Does that make sense? Okay. We want to describe the molecular transport of the velocity. Here's an example of the temperature. It's a better drawing than the one that I did. Here's t equals 0, that's the blue line. And at t equals 0.25, the very first thing that happens is it carves out that curve here. Now, I guess I should, oh, it's okay. All right, temperature's low and temperature's high. Yeah, it carves out here. And it's attempting to make it into a curved line. This would be a diffusive equation for temperature that doesn't have that form. Right? It would be a single derivative. Because here the slope is 0. Does that make sense? So we're holding one side cold, hot, and one side cold. If you didn't hold one side cold and one side hot, then what would happen? You just had a single rod. Like let's say you have this hot here, or sorry, this cold here, and this hot here. You don't keep these two fixed. You let them be whatever they want to be. What shape does this want to become? Right? At some point, it's going to come down to 140 across the line. Okay. This will be the trickiest part, and we will have trouble with it the whole year. Okay? We are going to describe something that is very non-intuitive because we don't live in a molecular world. I mean, we do live in a molecular world, but we are not in the molecular scale, right? We don't understand it as well. We're going to describe something called viscosity and diffusivity. And we want to think about, in particular, the word viscosity, which we kind of use as incorrectly. We kind of use it as like, oh, it just means stickiness, right? But really what it is, it's about how we transport velocity within a fluid. And I'm going to say that a couple more times throughout the semester so you really get to understand this, okay? So I didn't bring my book today, but if you had your book and you like pull on the top, you see that you can drag the whole book, right? Whereas if I have a fluid and I drag on the top of the fluid, I can't push the whole fluid over, right? So let's say I apply a force in a certain direction, like AB, right, at the top. How does that then transport into the fluid, right? Something is very efficient at transporting forces, we say that it has a high viscosity. If it's inefficient at transporting velocity, we say that it has a low viscosity. And I'll show you this when we see the actual equations, but it's going to be this little symbol, right? Oh wait, no, that's not right. This is the force. This is the stress symbol. There's another one I'll show you in a few seconds. Okay. Another way of thinking about this is, and this is one we can do, and you can do this at home. You have coffee, for example, and let's say you have your coffee and you just poured in a little bit of milk or whatever, and you want to mix it, right? So you do this. Okay. How did I get the cup to rotate the water? Okay, yeah, let's think about that. So I do this. Now it copies the motion. So what about the fluid, right? What is the property of the fluid that allowed it to copy what the cup was doing? the viscosity, right? It was able to transport the velocity that I gave to the edge of the cup and transport it into the fluid. So let me ask you another question. Let's say you have a viscosity-free fluid. Yeah, and then I try to rotate the cup. What happens to the fluid? All right? That's kind of a weird thing, but this is what happens with supercooled helium. So supercooled helium is basically inviscid, which means that it has no viscosity, and therefore just doesn't transport. And it's really hard to you can't spin it around or rotate it in any of those stuff. But you can pick it up, still solid, obviously, but it likes to even crawl out of its containers. So you make a little cup, has surface tension, and then it's like, wait a second, I really want to be on the other side, and it just crawls out of its cup. Okay. So the way that we describe the viscosity here, we call it the dynamic viscosity, and this is Newton's law of viscous friction. So when you say that something is a non-Newtonian fluid, what you're really saying is that it doesn't behave the way that this derivative is supposed to. Okay, so this gradient describes how Newtonian fluids distribute stress. Not all of them do. One great secret that I want you to sort of take away from the study of fluids in the last 200 years is that we are approximating a lot of what we see in nature. Okay. So for example, this equation right here, this is not given to us from on high. Right? What people do is they watch different things and they say, oh, it looks like the rate of change of the function is proportional to something times the shape that it had. Or in that other example with temperature, they say the rate of change looks like it's proportional to something, this first derivative, to the slope. Right? For some fluids, particularly annoying non-Newtonian fluids, it neither goes as the first derivative nor the second derivative, but some other derivative. Okay? So this can be very weird because you have sort of all of the standard looking fluids, your waters and your oils and stuff like that, and you can do lots of experiments with them, and they mostly seem to follow one set of equations. And then you have other weird stuff that have weird molecular interactions, and they just do diffusion different, or they do viscosity different, right? Because of the fact that they are not fully controlled just by bouncing billiard balls, but billiard balls that can attract each other. Okay? That's the major difference. If it was just billiard balls bouncing into each other, all of the collision stuff would work. Okay. This quantity is not mass dependent. We'll see more of that in a few seconds. Here's surface tension. Isn't that cool? What is that? What? Is it? Glass and ice. I heard glass and ice. Not correct.
Looks like when those spiders do their webs underwater.
That's fun, but not correct either.
Oh, water in space.
Water in space. That's correct. So this is on ISS. What he did, he blew, drank some water, blew through a straw to form a little bubble, and then he spun it. Okay? Now, why did he spin it? Why did he make it rotate? All the bubble would come down to the middle. Well, just because they're getting flung out, right? But as you do this, they sort of shape themselves, and what it's trying to do here is it's trying to create a boundary, right? So remember we talked on Monday. We talked about this idea. You can tell the difference between up and down in a fluid because sometimes you'll have a layer that forms. For example, you go to the ocean, The water's on the bottom, the air is on the top. When you remove gravity, surface tension, you do lots of fun things. Because now all it cares about is creating a surface that separates it from things that are not it. Right? It much prefers to bond, that is to say, not really bond, but to be attracted to the things that are it. Right? So here at the boundary of this fluid, it forms a sphere. Of course, the sphere is the preferred shape because all of the forces are inwards, right? Even when you have gravity, like let's say it's falling, you still form spheres. They're just kind of oblong. What shape are teardrops? Sorry, not teardrops, raindrops. Are they the picture that they show in the emoji? Is it this? No.
They're like wider.
What? It's very, very barely wider at the top. But that doesn't make it as cool a picture. I mean, does the heart look like this? You know what I'm gonna draw, right? Yeah. Okay, this is the heart, this is the star. Are any of these correct? Yeah, I guess this is with my drawing, it might be. No. No, so the droplets tend to be spherical, even in partial gravity, right? So if they're falling. Of course, you don't get droplets forming if they fall. You just get flat surfaces. But even in those flat surfaces, you get boundaries. And we will see certainly some of the actions, the interactions between a fluid and a wall can be quite unique. So for example, if something is hydrophobic, that is to say, it doesn't like interacting with water. Have you ever seen a hydrophobic fluid? Okay, I will encourage you tonight, go home, get a bunch of cinnamon, and I know you're thinking, don't stick it in your mouth. Okay? It's not what we're doing. But what you can do is take a spoonful of cinnamon, okay, and then just pour water. Not like a whole jug. Like drip water. Yeah. So it's hydrophobic. So it'll bead off. So here's your spoon. Okay. Here's your cinnamon. Okay. And well, it's a pretty good picture. I'm an artist. Okay. So we drop a little droplet of water. Okay. And what, let's say, let's take 2 examples. There's your spoonful of salt. So what's the expectation when you drop the water on it? Yeah, it absorbs, right? And it's gonna like land and it's gonna go. But when you drop it onto cinnamon, what it'll do is it'll hit, it won't want to absorb. The surface tension will be like, no way, fuck you. And then it'll roll. And as it does, you'll notice cinnamon on the bead as it rolls off. Now you wonder how we make cinnamon stuff? You just mix it and it gets over itself. Cinnamon can mix into water. Water doesn't want to mix.
So what about?
What?
Like what about?
Oh, that you're asking chemistry? Oh. I don't know chemistry. I know that it works. I don't know why it works. Okay. So this is what we call hydrophobic. I know in 2025. Okay. Hydro meaning water, phobic meaning afraid. And if you, for example, have fluid that's hydrophobic, you can sometimes get this, which is pretty weird. So if you have some sort of container, you might have the fluid here, and it will avoid the walls. And it'll bend in. Whereas sometimes you have like a normal glass, and you can get this situation where it'll climb the walls. Right? This, for example, is an example of capillary action. So how do trees get water to their leaves at the very top? Let's say take a 400-foot tall tree. Never thought about that, huh? Tree. Okay, don't comment on my tree. This is the truth, okay? This is mean for scale. Okay, very small. Now, if you've ever done statics, one of the things that they ask you to do is what's the tallest straw you can make? You know how to calculate it?
Now, it's not big.
You should know how to calculate it, and I'll show you how to do it in 2 seconds. So we use Bernoulli's equation. Remember that? 2500, 2510? Oh boy, gotta dust that one off. So it looks like it looks like this. Something like that. Heat. Is that word? Oh, let's say you have some tubes, like a barometer. Okay, and then the height of the fluid here tells you the pressure outside. It goes up. So you might use that, like, for example, in a plane, or as you go up a mountain, it tells you how high up in the air you are. Because as the pressure goes down, right, out here, and the column rises or falls. So this thing here tells you the maximum height of the straw. Because at the very top of the straw, you assume you have no pressure, like suck out all the air. And at the bottom, you have full air pressure, 1 bar. And then you get an inch. And it's something on the order of tens of feet. So I've seen trees taller than tens of feet. Are they sucking with more than 0 suck? Right? Do they have negative suck? No. So it can't be that they create a vacuum. Right? Even if they created a perfect vacuum at the top, they can only get water up tens of feet. And yet I've seen hundreds of feet tall trees. Air holes? What do you mean?
When they say capillary, right, that kind of means like tubes.
Tubes, yes. Good. So it does mean tubes, but we want to use something about the tubes. We're going to use a very special property of the tubes. Already good. What are these?
No, I said.
It's a tree.
Oh, I
this
said
one.
one of those, yeah.
Yeah. We're going to use surface tension. We're going to use the fact that the water likes to decline. So I also encourage you to do another fun experiment today, and this is one that you're probably unfortunately familiar with. Take a paper towel, okay, hold it above a thing of water, right, and then just dip one edge of the paper, just the very, very tip of it. Why? Why does it climb? How the fuck does water climb a paper towel?
Oh, paper towels like water.
Paper towels don't give a shit about water. They don't know anything. They're sitting there living their own life, and all of a sudden they're drenched, right? Why can water climb up a paper towel? It's very powerful, and yet we really don't think about it that frequently. We tend to think about it only in the context of, oh, it's kind of fun, this thing, like a little bead dropped off off the cinnamon. No, it's immensely important for thinking about interactions between surfaces, for thinking about interactions within a tube, with interactions in biophysics applications, right? Okay. Questions, comments, concerns? They also depend on the fluid. The water, oil behave differently, different surface tension. What's an example of a strong surface tension? What? No, yeah. That would be correct, but for fluids. Yeah. I want an example of a fluid with strong surface tension. Yeah, so that's an interesting thing, right? We have an instinct, right? That says something that runs poorly must, or something that like doesn't flow very well must have strong surface. And yet we don't quite know if that's true. If you compare, have you ever drank wine? Have you seen wine? Okay. Have you ever noticed that you can tell if someone is drinking wine in a film based on how the wine adheres to the glass? So alcohol has a different viscosity than water, which has stronger surface tension. No, it's a question.
Oh, which question?
Which, alcohol or water? Why alcohol?
Because it's able to adapt to its, better.
Yes. Yeah, I would say that almost exactly the same way. I would just say it just holds on, right? It's like a climber. It's up there with all its friends, and then after all of its friends have sort of fallen off the mountain, it's still hanging on, right? So the surface tension of alcohol is actually greater than the water. Now, you would look at those both, and you would never assume that one flows faster than the other, right? So I would have, because you were thinking of like, oh, you know, a tar or something like heavy and thick would have a higher surface tension. So what I'm trying to do is I'm trying to separate those ideas. So we have been throwing these words together, viscosity, you know, just throwing everything together and saying, oh, if it's sticky, it's viscosity. And what we're going to need to do is we're going to need to separate them all up. Because not only are we going to find that there are different types of viscosity, right? There's different types of surface tension. All very stupid and unknown. Okay. But that's the best part about learning. Okay. Oh yeah, what's gonna happen here? Wanna watch surface tension? At 2500 FPS. So this water is gonna hit. Gonna hit very normal speed. We're gonna watch it in slow motion. What's gonna happen when these two surfaces interact? What? They're gonna grab each other. What do you mean by that?
They're the same type of molecules, they're going on the bottom.
Good. So you're saying what we're. And we'll have to like make experiments before we get to watch fun movies. This is gonna hit, and then it's gonna whoop. Is that true? Okay, so you want to go like this, whoop, and then it creates a little thing from the bathroom, and then whoop. Is that it? Never seen this before, right? You're all wrong. So it's every day anyway. Let's see the second. All right, let's watch it. It's fucking awesome.
Hello, the internet. We are here with. All right, Dan.
No one cares about that.
Started without you. They got me there. Hi, internet, right? Yeah, Dan says hi, and so do I. Now we're going to do a video about little droplets of water that land right on the surface of the water. They're not going to come from high up. They're just going to tip on, and we're going to. How's it?
There
There
we
you
go.
go. Nailed it.
All right. Yeah, that seemed like it worked, right? What happened? What happened? This thing going in. It's just sitting on the water. Oh, interesting. Would you have guessed that?
Watch that. Probably looks cool.
No,
Oh.
it looks cool. That's why we watched it, bro. Okay, hold on. All right. Yeah, so here's the picture. It's an actual picture. Let's a really shitty one here. Tallest redwoods are 370 feet. Pretty cool. The free surface of water in it too, we saw that over there, is curved. It's not how strong the obviously. The source tension is pretty important. This capillary effect, I think I already smashed that over the head. But do you have questions on this? The one thing you may be asking yourself is like, why do we use pumps to get water uphill? What? Well, so the question is, you know, if water can climb up a paper towel, water can climb up a tree, why don't we just let it climb up some rods? What do you think?
Slide off. Or-
But if you made like really, really thin pipes that go all the way up the mountain.
There still wouldn't be a vacuum to open it up.
Yeah, they don't have vacuums. Trees don't have vacuums. They use only the capillary action. This is really important, right? They're not drinking the much, they're not like LA, right? So you want to pull up the amount of water that we need to get over a hill. You can't use capillary, it's just inefficient. It's free, but it's inefficient. That make sense? Okay. Here's another example of capillary action. You see what I see? On the left-hand side is a big old glass, and the glass, of course, you can see that it is not hydrophobic. It's hydrophilic. It enjoys the interaction with water. And look at the curvature, right? See that there? Now, as I make the tube smaller, it can grow taller than the height that is permitted by gravity. So this extra growth here, or extra like traveling up the tube, is due only to capillary action. And when I make it nice and thin, whoop, it's very high up there, right? But of course, very thin also means that you have a very small amount of fluid. So necessarily, this is a bad pipe, and this is a good one. Right? And also fixing this, like, can you imagine? You just get like a small earthquake, and then all the pipes are snapped and they're broken. Okay. We are gonna start on Monday, probably talking about statics. So I would strongly suggest, if you don't remember this section from like what Bernoulli's equation is, that type of work, it's a good idea to go back over. We want to think about things like pressure, like the ability to write that out pretty quickly is fairly important, because we're going to use these ideas in order to demonstrate how fluids at rest can be converted, how we can use the mathematics of fluids at rest and turn that into fluids in motion. In this question here, P1, P2, and P3 are all acting on different sides of a fluid at rest. My claim is that the pressure here is equal to the pressure here is equal to the pressure here. Is that true? Why if they're all the same length? Yeah, it's an interesting trick, right? I'm going to pull a trick on you. Okay? So because it's at rest, I'm claiming that it's at rest. This is an arbitrary angle. I can show you an extreme version of that, which is certainly is true. And from there, we'll have to determine that it's always true. Okay, ready? So the first thing I'm going to do is I'm gonna lengthen this tremendously.
Mhm.
Such that the angle gets really thin. And ds starts to approach dx.
Mhm.
And in the case where ds and dx are equal, then how is P1 and P2? They must be, right?
Mm.
Okay. So that means that nothing is moving up and nothing is moving down. So now let's add a contribution only from the left. So even though it's a tiny, tiny, tiny bit of area, it now has to hold up all of the fluid that's pushing it to the right. Right? So, and we can show this mathematically next time, but this is the type of proof that I want you to become familiar with, because it will be non-intuitive, right? And in particular, we'll say, oh, the sizes and the pressures, no, that can't possibly be right. But when we start to work them out, we have to think about the fact that the pressures, there's scalar quantities like energy. And yet, we're going to apply them in the direction of objects. So just like before, when we had forces acting not only in the direction, creating pressures and rarefactions or contractions and expansions, we're also going to have stresses going in opposite directions, right? So if we don't understand them in a static direction, in a static context, we're going to have a really hard time when we get into tensors, okay? Okay. Yeah, we got some time. Other things that we'll do, make sure that you have done a little bit of your classical thermo, just like brush that off, because we'll talk about these. We'll talk about state and path, and then we'll talk about, you already did this, so that's great. That's what I said at the bottom here. No, that's all. Almost all of you have turned it in, right? Okay. I'm gonna provide homework 2. It'll just be on the stuff that we've done. Okay. And some fluid statics. Review of 25.